I think I also have to admit people. But okay, it's now being recorded. So
Okay, perfect.
yes. So thank you very much, Thomas, for introduction for us. Thank you very much for inviting me for this virtual talk. In fact, having such a series combined with virtual talks is actually not such a bad idea. It prevents people traveling a long time for giving a talk about an hour. Although there's nothing wrong with going to Vienna, of course, but uh, maybe for certain other reasons as well. Um, Also, we have been in the office for a long time now, but our online work continues, and therefore I think it's quite normal to have these kind of uh, online presentations as well. So thank you for attending. As Thomas said, I could select my own title, in fact, for professorship, which is on multi-hazard risk dynamics, so how the risk of multi-hazards changes over time. That is a real research challenge, both in terms of the multi-hazard analysis, multi-hazard risk, as well as how that changes over time, both in a long duration and related to climate change, global change, as well as over short periods of time, for example, after the occurrence of a major disaster. So I have, say, research interest in how we establish multi-hazard risks, and one of the fields is also looking at how we can do this at different scales. And so one of the scales that I have also been working on in the past years is on the national scale. And since we are an organization working a lot in developing countries, or actually primarily in developing countries, at least not in the Netherlands, let me put it like that, we also tend to come across a lot of situations where there's really issues with data. Now, that might not be so extreme for the country where I'm going to talk about as compared to others, but this is a problem which is faced, I think, more than one would think. So my talk would be about assessing, aiming at assessing multi-hazard risk at the national level with a specific focus on data poor regions, and taking the example of Tajikistan, Central Asia. Okay, so I would love to go to the next slide. Yeah. So multi-hazard risk assessment is is one of the tools, but a basic tool for decision making um, by different stakeholders, but also at different scales of analysis. And these um, types of objectives could be completely different, whether they would be for spatial planning, for risk reduction planning. It could be planning of critical infrastructure, maintenance of critical infrastructure. Could be focused on financial aspects, on risk transfer, on early warning, or prioritization for support, for funding. Um, And each of those objectives, and there are many more objectives than those, but they would have their own requirements in terms of what kind of data would be needed, what methods for risk assessment would be most appropriate, uh, and also what combinations of hazards and elements at risk should be analyzed. So the picture on the right, a bit complicated, but looks at a risk management framework where in the center of the of of the framework is the actual risk analysis with its important components on elements at risk, hazards, and vulnerability assessments. But as a tool for doing planning on alternatives, risk reduction alternatives, and looking at the effects of future changes. And so this is the framework under which we do this type of analysis. So these decisions made by by stakeholders in order to use risk information could be really diverse, and they depend also very much on the, the scale of analysis. So ranging from international to municipal to even community level scale. The aim of the work you do, the projects that are done on risk assessment have a very different aim. Yeah, whereas, for example, in the international and also a lot in the national scales, maybe prioritization would be the key word, where funding agencies, international funding organizations, World Banks and ADBs and all these different organizations aim to look at the prioritization for countries for their funding mechanisms, but also international risk transfer and also for large-scale risk mitigation. Whereas if you go to much more detailed levels, it would be much more about spatial planning, about planning of infrastructure, about early warnings, preparedness planning, etc. So each level of analysis will be related to its own objectives. So the scales of analysis matter very much, and also the tools that have been developed with with respect to risk information are diverse. At global level, you see a lot of developments, both in, would say, the global risk assessment, as well as the components needed to carry out such risk assessments. Take as an example here the global risk data platform, which was made for the GAR 2015 and shows, say, quantitative estimate of multi-hazard risk, looking at basically earthquakes, tsunamis, tropical cyclones, storm surges, and riverine floods globally, but at a particular scale. So with the cell sizes that are sometimes 10 kilometers or 5 kilometers large. And so when you zoom that into a national scale, this is not an appropriate scale anymore. So at that scale of nations, a different level of analysis have to be done, basically also with different types of input data. And many countries have been doing this. A lot of European countries do this by themselves. They're supported also by EU in this. But many developing countries have difficulties in setting this up, and they are then supported by international initiatives like World Bank or the development banks of the different regions. So we we have also been involved in a number of those studies. For example, in the Caribbean, we did this for 5 countries. We did it in the Caucasus, and now we do it also in Central Asia. And one of the key aspects that you come across there is the basic lack of data. And so you would say, are these some countries really data poor? Especially in terms of historical disaster data information. Of course, we would all go through EMDAT and Desinventar and these type of disaster databases, but these are by far not sufficient to be able to do this type of work in those countries. In many cases, Desinventar is not implemented in those areas. And historical data is at most collected by a national agency linked to emergency response. So very response oriented, and also very often related to Ministry of Internal Affairs or Ministry of Defense. And so also rather closed organizations. Elements at risk characterizations are also a huge problem, whereas many countries are getting filled now with information from OpenStreetMap, where you can directly grab building footprint information and use that in your analysis. Many other countries have very poor information related to that, even though mapathons are being developed, but then mostly after a disaster has happened. And also in terms of hazard data, there's a big shortage. So if data's there, it's often missing. Take in our example when we look at Central Asia, it was part of the Soviet Union for a long time, and during that period they had extensive measurement networks, for example, discharge or rainfall or historical events, and that kind of stopped after their independence, and it's only slowly starting to come back. So there are huge data gaps. It might also be restricted in many cases due to the semi-military nature of these organizations, these Commission on Emergency Operations, for example. They are not open to sharing these kind of hazardous data with others. All these are updated, so most of the maps we got for Tajikistan were really made in Soviet times, or they're simply wrong, as we will see also later. So in response to a call from UNDP, we partnered with an organization with whom we work a lot of times, with the Asian Institute of Technology, which is in Bangkok, Thailand, but which is a kind of similar type of organization as ITC. We are Organization for International Capacity Building. They focus mostly on the Asian countries. We have our clients, our students from all over the world, but they are they also are active in the niche of geoinformatics and disaster management, and we kind of enforce each other. So we do quite a bit of these type of joint projects. And we decided to react to this call for proposals by UNDP in Tajikistan, where the aim was to assess the risk of communities and infrastructure to a whole series of hazards: earthquakes, landslides, floods, mud flow, snow avalanche, windstorms, and drought, within basically less than 1.5 year time. And it should be mostly based on available data that was present, or international data. So project was not such that you could collect information on the ground for such a huge country of about 142,000 square kilometers, so really, really large and very mountainous. The other aim was to develop risk profiles for the administrative units of the country, which would be the basis for their development planning processes. And so the analysis had three components. We developed this risk assessment methodology, we built capacity of local experts, and we developed at the end the disaster risk information system. So an online tool where all the results of the system of the project can be consulted and downloaded. So the right hand here shows a bit the overview. We looked at hazard maps. We worked with it in a way that the hazards are classified in terms of intensity and frequency classes. So we could use a kind of uniform methodology for all of the types of hazards. We linked that to physical vulnerability, and we had 4 types of elements at risk that we looked at: buildings, people, roads, and agriculture. And so we looked at the combinations that were relevant, because not all combinations were relevant. So we generated risk profiles, and then we did that per district. Say, Tajikistan is built up of provinces, and then below the provinces are the districts, and within the districts are the municipalities, or the locally called jamawats. So the this is the framework of the analysis that we did. we started with a number of maps that were that we had to generate in terms of hazard maps. So we were able to model hazard intensity and frequency for earthquakes, for droughts, for windstorms. Sorry, this mudflow should be floods. So floods, earthquakes, drought, and windstorms. And for the other types of hazards, we are only able to derive susceptibility maps. So for landslides, mudflows, and snow avalanches. We estimated spatial probability of the events as an important component of the analysis. So the chance that a particular location within a particular hazard zone would be affected by the type of hazard within a particular return period. And that is one of the important components in estimating the risk, as it is composed of the probability of the event happening, the spatial probability that an element at risk would be in fact damaged, affected, the degree of loss, so the vulnerability part, and the quantification of the exposed elements at risk, so the exposure part. And so within this risk calculation, we had to look at all these 4 components, where the probability of the events happening came from frequency analysis, mostly looking at the triggers, be it, say, wind, earthquakes, rain, as major triggers. The degree of loss came from a physical vulnerability analysis, and exposure analysis came from analyzing the relationship between the elements at risks and the hazards. So we we generated then at the end risk profiles per district and stored them in a WebGIS. So we started this project with inception workshops and trainings, as it's normally done, visiting all the state organizations that are responsible for a particular type of hazard, and also creating awareness of our project, and also creating some kind of trust, because initially there's a lot of mistrust when you come in as foreign experts and say you want to do this, whereas the national organizations should be able to do this equally well by themselves. So that's why we said we want to collaborate with you, and if your experts provide the national scale maps, that's even much better than if we have to do that for you. And so later on, we did also extensive training, where we then focused much more on the younger generation of people within those organizations. So 2 weeks training, focusing on the different components. So we made different working groups, for example, groups on hazards or groups on element at risk generation. And with those groups, we try to keep contact and develop the individual components later. We started then with collecting information related to hazards. And so hazards, we were asked to look at these 7 different types of hazards. And for each type of hazard, we developed maps that would explain, give information about frequency and about intensity. So intensity was generally modeled as continuous values, but then were reclassified into classes to make the procedure more transparent. So these intensity class could vary also from hazard to hazard. So there were 3 hazards that don't have frequency or intensity classes, and then those also spatial probability in relation to return periods would be relevant. So which would be translated basically in what would be the density of those events with a return period of 20, 50, or 100 years. So we had different teams working on those on the various hazards. And in the earthquake hazard assessment, yeah, Thomas, you would like to ask something? Okay, well, you have your mic on, so if you want to interrupt me, please go ahead. I hope you're still hearing me.
Yeah, well, that's exactly the point. Sometimes it's a little bit interrupted. Possibly it's better to switch off the camera.
Yeah.
Because your camera is still switched on.
Okay.
Thanks.
Okay, I hope that will improve it. So the first group was dealing with the earthquake hazard assessment, and that was done by local national experts, led by national expert Anatoly Ishuk. And they followed, say, the conventional method of probabilistic seismic hazard assessment, where they looked at the historic seismicity and cleaned the data set for historical earthquakes, then looked at earthquake source identification, defined the seismic recurrence characteristics, applied attenuation functions, and then came up using the calculation of ground motions using the Crisis 2015 tool, which estimated then the peak ground acceleration and spectral acceleration for different return periods. So at this national scale, no soil or topographic amplification effects could be taken into account. That would be not possible at this the national scale level. So the output of our earthquake hazard assessment consisted of maps of 3 return periods, say standard kind of output done for probabilistic seismic hazard assessment, with 100 for 75 and 1,000 year return period, where we had PGA maps and spectral acceleration maps of 0.2 seconds and 1 second. And so these were generated for these various return periods, and in the methodology we used the classified PGA map into 4 different classes. The second group was working on drought hazard assessment, where ideally we would have like to use the historical rainfall data from the country itself. Unfortunately, the meteorological department was not willing to share their information. And so we used other data sources for rainfall, and we had, for example, the NSIDC and Global Historical Climatological Network information, where we got data for a period of time for 62 stations. And we used the SPI method, Standard Precipitation Index, which quantifies the precipitation for different time scales in a standard probability distribution, which goes above or below a 0 line, and below the 0 line indicates possible drought conditions, and above is wet conditions. And so the depth of the area of the below 0 would indicate what would be the severity of the drought. There, an SPI generator software was used from University of Nebraska. So the drought hazard map was prepared at 6 months time scale, so you could do this at different time intervals to look at the seasonal and medium-term trends in precipitation. So the magnitude of the drought corresponds to the water deficit over the drought period. And we did a frequency analysis based on the drought magnitude over the time period to get an idea of the return periods for different SPI values. So the result was that we obtained drought hazard maps, which we did for 3 different return periods, here shown only for one of the 5 districts, regions within the country, and classify these SPIs also into, in this case, 5 classes. The next hazard we looked at was wind hazard, and also that was a major difficulty because of lack of wind data from the country itself. However, we used different data sets. One is GSOD from NOAA with 44 stations that have wind, also with wind gusts. And importantly, most important type of information, we used the ERA 5 reanalysis data. So modeled estimates of many meteorological parameters at 30-meter grid size for a large period of time in the past, using, say, climate models that are also used for modeling future climate change, but then adjusted also for historical information. So this gives a constant and data set over a large period of time, but at a rather coarse resolution. And we used also what's called the Global Wind Atlas, which is modeled wind data by a number of organizations that are basically looking at wind energy possibilities. And so they give us the mean wind speed over a particular area at particular heights above the terrain. So we used the ERA 5 wind data and compared that with the data for the station data. They seem to correlate relatively well. So we eventually used the ERA 5 wind gust data at 10 meters and then generated for those, say using extreme value distributions, we generated the extreme winds for different return periods. And the Global Wind Atlas information was used to smoothen that information at the lower scale. So we used the Beaufort scale to classify these hazards, and so we got eventually our windstorm hazard maps for different return periods. Then our flood hazard assessment was done also at national scale, which was a major task. There we had to also collect national scale thematic data like digital elevation model. Originally we looked at Alos Pulsar 12.5 meter dam, but that was hydrologically very problematic. So eventually a 30-meter SRTM was used, which was also used to derive basins and river network. Land cover data was used from different sources and integrated into an updated kind of land cover map, although with a relatively small resolution. Soil grids, that's a global soil database developed in Wageningen in the Netherlands. That's based on a large number of soil observations and geostatistical analysis, and that provided good estimates of a number of physical soil parameters. We also used the ERA 5 reanalysis data, in this case, the daily rainfall, to analyze what would be the frequency of rainfall amounts within different grids. And we had also time series of discharge for limited number of stations for validation. So my colleague Bastiaan van den Bout did the analysis. So first the statistical analysis of triggering rainfall, and then a physically based approach with a rainfall runoff model, where he decided to select two different models working at two different scales. At the national scale, he was working with a model based on the PC raster software, dynamic GIS software developed by the University of Utrecht, but which is also being used quite a bit, for example, in Europe by JRC and others, where it's called ListFlood, but it's based on the same software tool. And at the local level, he used the OpenLISEM multi-hazard software tool that has been developed by our group locally. That model is much more powerful, but cannot be applied at the whole country scale. So based on those two scales, also two different types of products were obtained. So first, the frequency information was obtained from the ERA 5 data analysis and fed into the hydrologic model. So then having a rainfall runoff model for different return periods at 200-meter pixels, which was kind of rescaled to 30 meters. At the local level, the modeling itself was done at 30 meters, but only for selected catchments. And it fitted very well with historical information. So this is an example of the resulting flood hazard maps. They were classified into three classes, also in relation to the damage the flooding would give to the different elements at risk. So our hazard types with intensity frequency information were these four different hazards, and also with their corresponding return periods, which were not necessarily the same for each type of hazard. For example, for earthquakes, these return periods are much larger. Then we had also three other types, which we could only derive susceptibility information, and we had to convert those later into maps representing return period, and that's a phase where well, quite some subjectivity came into play. So because that comes around the idea of spatial probability. So this are landslides, mudflows, and snow avalanches. So landslides is a major hazard within Tajikistan. There are a lot of landslides, but there is not a very good landslide inventory available. So we first try to obtain landslide inventories from different sources and combine them together, but they are really incomplete in the sense of some areas are very dense, as the one shown in the picture below, but that's because it's close to a hydropower dam, lake. And so that's where they did a lot of studies, whereas a large part of the rest of the country is very limited. But if you check that with Google Earth, there are also lots of landslides. So the distribution was too limited to really use statistical analysis as a basis for susceptibility assessment. We did use it, but then only in an exploratory manner. We also tried to look at how we could incorporate earthquake-induced landslides. Here's an example of one of the earthquakes that hit the country, the Geit earthquake from 1949. And this actually is the only earthquake we found where they had generated an earthquake-induced landslide inventory map. And so these were added to the database, but for other earthquakes like A very major one happened in 1911, which caused the famous Lake Cees, a huge dammed lake with a huge, one of the biggest landslide dams in the world, Usoy Dam. But for that, no other inventories were available. So it's really hard to make the link directly between earthquakes and landslide occurrences. So we used instead a spatial multi-criteria evaluation method where we integrate the different factor maps, both in terms of causal factors as well as triggering factors. And we use standardization and weighting and use the available landslides to validate our results with. So you get a typical example of a map that would look like this. One of the most landslide affected areas, it was the same as the one where we saw all the points before. The point is now here also is, okay, when we are in a particular district and you're in a red, orange, or green area, what would be the density of landslides with a triggering event once every 20, 50, or 100 years? And that is the essence of what we would do later in estimating spatial probability. So similar, a problem was in the runout part, looking at mud flow susceptibility assessment. Mud flows are really a big problem within the country of Tajikistan. They are really massive events. I could, if possible, show one example, if that's possible, on YouTube. Here you see one of these typical events, mud flow events that are so powerful that they could even dam a major river, as you would see here. And so they are events that are caused by different processes in the upstream catchment, entrainment, dam breaks, landslide dams could be, but also in some cases also ice dammed events. So these events are, okay, sorry, let me switch this off. Yep, these are very frequent in the country, and they also cause a lot of damage. So for this particular event, types of hazards, we had a previous work also done by national experts, indicating here this is their inventory map with the major problem areas. But then when you do careful interpretation of images, you'd see there are many more than those. So we did our own mapping of mud flow source and deposition areas in the country, which was more feasible than to do that for the landslides. So this would be our resulting mud flow susceptibility map for part of the country. Again, no probability, no intensity. Finally, snow avalanches, they were obtained from a national expert. So he already made this map. So we, we decided to use this map with its explanations directly. So in total, we had then all our hazard maps, return periods for drought, flooding, windstorms, and susceptibility maps for the other. Then the second component was the elements at risk, where we were mapping, started with mapping built-up areas. We wanted to look at, say, settlements, not at the level of individual buildings, because we already knew that that was not a possibility, given that the majority of the country has also no information in OpenStreetMap. And so we had to do our own assessment of built-up areas and then translate that into types of built-up areas and then into number of buildings. So we made a combination of cloud-based image classification where deep learning approach was being used to separate built-up areas from non-built-up areas. And then crowdsourcing was done to outline the exact unique homogeneous areas and assign a number of classes related to types of built-up area. So this was done by a tool that was developed by AIT, where it divides the area in blocks and people get a certain block to map, others validate it. And based on that, say the settlements were being mapped and were also being checked by others in the quality control. So this was done for the entire country. So this was a major effort involving quite a bit of people to do this. And eventually obtained a settlement map, which was not yet available in the country. So these settlements were then classified into 5 types related also to the type of buildings that were present. So single-story rural, single-story urban, multi-story urban, industrial, and other buildings. We then had a group of people doing samples. So they took samples of the homogeneous units and counted the number of buildings within those units. So here are, for the different types that we looked at, how many samples were taken. So 250, for example, for low rise. Yeah? And so based on those samples, eventually calculation was done on what was the average number of buildings per hectare or per square kilometer within one of those 5 land use classes. We also used that estimation, which was tested also for a number of sites, where we had the samples, but also where we had we did have OpenStreetMap information. We then also estimated the number of people and adjusted that based on the census information that we had. So we had only census information for administrative units, but not for the individual settlements. And so this was done to do this kind of decimetric mapping approach. And agricultural areas were also obtained using crowdsourcing application on top of classified images. So that had been done by international initiatives where they had classified the agricultural areas, and they were later checked by a team of mappers. And so we ended up with 3 different classes: those that are within settlements, they are only coming from the satellite image analysis, and those that are confirmed by visual image interpretation. So we did not include types because of the large areas. We could not characterize different types of agriculture, and also not whether it was irrigated or non-irrigated. One major issue that we came across when we did this work was that, say, the administrative units within the country were all wrong. So when we were given initially these maps by the national organization, when we overlay them on top of your settlement maps, it appeared that several settlements would be in 2 or 3 different municipalities, and that also municipal boundaries would run very strange in relation to the features in the topography. So it was obvious that these were completely wrong. So we actually asked the national organization for land administration, FASO, to prepare an updated map, which they did in the course of this project. One of the problems related to that is that also all the indicators coming from the census data were difficult to use because the boundaries of these admin units were completely wrong. The next step in the analysis that we did was a vulnerability assessment. So as a component of the risk analysis, vulnerability is evaluated making use of existing vulnerability curves, relating that to the building types that we would have within our 5 classes, and translating that more or less into a matrix. So where we would have our intensity classes, our types of elements at risk, and then we would use kind of matrix instead of curves. So we did this type of analysis for the combination of all hazards and elements at risk that were relevant. Some were not considered relevant. And so here an example is given for flooding, where you would see the classes used in flooding depth and the degree of damage that would be in rural buildings, low-rise urban, high-rise urban, crops and roads. Information from that was obtained from available vulnerability curves in international literature, but we used quite a bit of the work done by CAPRA. Also for the global risk assessment platform, they had developed this whole database of curves, and we correlated those with the types of buildings that we had available within Tajikistan in terms of urban low-rise, rural low-rise, and urban high-rise buildings. For flooding, for earthquakes, for winds, this type of information was available in a tool that's called ERN vulnerability. However, we still had to make a lot of adjustments and also assumptions. One of the difficulties, for example, was correlating SPI values with the effects of crops. That still is a major uncertainty. And for landslides, mud flows, and snow avalanches, since we have no intensity values, we can also not directly correlate physical vulnerability to the intensity of the event. So that involves subjectivity here. Another major difficulty in the procedure is to estimate if we have different intensity classes or susceptibility classes, what would be the actual chance that a building within that, or a road, or any element at risk would be actually hit by that event. That's called the spatial probability. And that represents, even if it is a modeled hazard like earthquakes or floods, if we would use all the exposed elements at risk for that return period, you would get extremely high losses, because you would generally not have that all the catchments within one district, for example, one municipality, would have flooding at the same time. On the other hand, also for the hazards for which we had no frequency and intensity information, we had to estimate the density of hazardous phenomena within a given time period and a given susceptibility zone. We tried to do this based on the historical records. So we tried to get information on historical events per administrative unit, which was difficult because we only had it for a limited amount of time. And so therefore had a large underestimation of those events, but also make an assessment of what would be the average size of an event if it would happen. So once we have all these components together, we could integrate this into our multi-hazard risk assessment. And this picture shows the general flowchart of this, where we would start with our hazard intensity maps. These are the return periods. The black are the ones that we had available. We have our susceptibility maps, which with historical data try to translate into spatial probability maps. On the other hand, the element at risk information, we did an exposure analysis. We aggregate the exposure per district. We converted intensity to vulnerability. And so we obtained a database here initially of the exposure that we used in the vulnerability assessment. And we had the vulnerability tables, as I showed you before. We then multiplied the exposure with the vulnerability and the spatial probability and obtained a loss database. So for each hazard, element at risk combination and return period, we have a loss. And then we integrated that into annual losses. So we could then compare annual losses between hazard types and elements at risk. So for the annual losses, so for the risk, by integrating the losses from different return periods, we used the so-called Dutch method, which is a kind of simplified method that estimates the area below the risk curve with limited number of events that are being modeled. So using that, we have an indication of annualized risk. So after developing this whole procedure, we made it into a risk information platform. This platform can be accessed through this website, and the platform has different options. You could query your hazard map, so all hazard maps for all admin units can be analyzed in this. You could query your elements at risk maps. You can do the exposure analysis for any combination and any admin unit. You do the loss analysis, and importantly, you could make a risk profile for any admin unit that you're interested in. So first, the hazard map querying. It's possible to select, when you take the option, to select any of the regions, or you can also do it for the whole country. Then the district, the municipality called Jamoat, and then a drop-down list of the different types of hazards. And whenever relevant, you get also information on the return periods. Each time you get also map information, but also statistical information, which you can click and get information on how much it is. You can change the opacity and change the base layers to combine it with different ways. In a similar way, the elements at risk information, again, querying your database on any combination of information that you're interested in and getting the these aggregated information, which you can also download and save and use it in other options. Then the exposure analysis, also here works in the same manner. You select first the admin unit you're interested in, you select the hazard, the return period, and then the type of element at risk you're interested in, and it will generate then the information, the map of the exposure, but mostly important here is the statistical information in relation to how much of the, this case, number of buildings would be exposed to those 4 classes of intensities for the different return periods. Also available as a table, and the table could be downloaded as a Excel sheet when people are interested in. Then the loss and risk part of the platform can also be looked at, where you would then get the both the losses for the combination that you're looking at, as well as the annual losses. And the important part in the in the platform is this application, where you can select your region and your district, and you can make your own risk profile. So for any combination of hazards, elements at risk, you will make a selection of what you want to look at. You see, you cannot make all the selections. For example, drought and number of buildings, we only consider drought to be relevant for agricultural areas in this. example. And so once you've made your selection, it will you generate the risk profile, and you get a screen that does this, and you could also download that as a report. I can just show you one example of that. This is, for example, if we do it for one district and one area for flood-related hazards, and once we generated it, this is the standardized output that you would get with the flooding maps, with the histograms, your elemented risk information, your exposure results, and eventually the loss results. And so these are different for any combination that you select for any area that the user is interested in. And this could also be printed as a report together with a binded cover and everything. So, people from different admin units can use this reports. Okay, so apart from the information in the platform, say the layers themselves can then also be downloaded through a GeoNode. So all the hazard elements at risk information, all the data that's being used within the platform are also shared through a standard GeoNode data sharing platform. So this is an example of a methodology in a data poor environment. It was the first of its kind at this scale in Tajikistan. And the aim is to prioritize districts with respect to risk reduction planning. So we refrained from quantifying the risk, for example, in economic terms, because there was really not yet enough information to do that. It could be used for analyzing possible effects of changes by incorporating, for example, the differences in terms of return periods of hazards, or by including different scenarios of elements at risk for future periods. The national organizations, they could update the data in the GeoNode. They can use the GeoNode updated data back into the portal. There are clear limitations of such a method. It's, of course, within a short period of time, involving local experts as much as possible, but not for all types of hazards turned out to be possible. Definitely, there would be more information available than you would be able to get out of that. So it's very much depending on international and local available data sets. And also it has a number of assumptions, especially those related to estimations of spatial probabilities in the absence of good historical data. So there are also things where it cannot be used for local disaster risk reduction planning, for example. But it's a basis for follow-up work, and I think in order to improve that, I think countries should be focusing also on their historical disaster occurrence data, for example, incorporating a desinventar, or doing more detailed hazard assessments at the district level. Obviously, also OpenStreetMap use of collecting information on buildings would be very good to do, so that at some stage we could move from built up areas into estimation of real number of buildings based on building footprints. And it would also be very helpful to incorporate local projects that had been done in the country and bring them to the national scale, so that you could also see in which admin units they had done more detailed projects. Well, eventually, the last thing is we wanted to also incorporate holistic vulnerability data in there. There was a database available with a lot of indicators related to population, to education, to economy, and to other sectors. However, that was linked to this erroneous admin unit. And so this would be a major new step to readjust this database based on the new admin units. So we refrained from doing that. That might be nice for a follow-up project. So with that, I think I thank you for your attention in listening to presentation. I also would like to thank all these many co-workers with whom we did this project, both from AIT, from ITC, and from Tajikistan and in other international experts as well. And I thank you very much for your attention. And I give back the floor to Thomas. And let me stop sharing and stop the recording.
Okay, good. Yeah, Cees, thanks a lot.